Have you ever wondered how we determine the spontaneity of adsorption processes? Let's dive in. Adsorption, that fascinating phenomenon where molecules or atoms adhere to a surface, is all around us. Whether it's water vapor condensing on a cold glass, or pollutants being filtered out of the air, adsorption plays a crucial role in our everyday life. But how do we know if an adsorption process is likely to happen spontaneously or not? Enter Gibbs's free energy of change. This remarkable tool allows us to evaluate the spontaneity and feasibility of adsorption processes. In a nutshell, if Gibbs's free energy of change is negative, we can expect the process to occur spontaneously. On the other hand, a positive value suggests the process won't happen on its own without an external push. Now you might ask, what does it mean for an adsorption process to be spontaneous? To understand this, we first need to decipher what Gibbs's free energy of change really is. At its core, Gibbs's free energy, denoted as G, is a thermodynamic potential that measures the useful or process-initiating work obtainable from a closed system at a constant temperature and pressure. It's like the energy reservoir that a system can tap into to get things done. Now when we talk about the change in Gibbs's free energy, symbolized as dG, we're referring to the difference in this energy before and after a process, in our case, adsorption. This difference is critical because it helps us predict whether a process, again, like adsorption, will happen spontaneously or not. Think of it this way. You're on a road trip. You have a certain amount of fuel in your car when you start. That's your initial Gibbs's free energy. As you drive, you use up some of that fuel. That's your process, or adsorption. The fuel you're left with at the end of your journey is your final Gibbs's free energy. The difference between the fuel you started with and what you ended with, that's your dG, or change in Gibbs's free energy. If you used up more fuel than you started with, your dG is positive. If, however, you ended with more fuel than you started with, your dG is negative. Here's where it gets interesting. If the change in Gibbs's free energy, the dG, is negative, it means the process will occur spontaneously. It's like saying the car can drive itself without needing a push. But if dG is positive, the process will not occur spontaneously. It's like the car needing a push to get going. So, in essence, a negative dG value validates a spontaneous process, while a positive dGO value is indicative of a non-spontaneous process. Quite a lot to take in, isn't it? But don't worry, we'll summarize the key points. We've delved into the crux of adsorption spontaneity and how Gibbs's free energy of change plays a pivotal role in evaluating it. Remember, it's all about whether the process is spontaneous or not, and that's where Gibbs's free energy comes in. The key takeaway here is the significance of the dGO value. A negative dGO value is a green light, signaling a spontaneous process. It's like nature's own way of saying, go ahead, this process can happen on its own. Conversely, a positive dGA value is a red light, indicating a non-spontaneous process. This means an external force or energy is needed for the process to occur. In essence, Gibbs's free energy is a fundamental tool in understanding adsorption processes and their spontaneity. So the next time you come across a discussion on spontaneous processes, remember Gibbs's free energy, and you'll be able to follow along with ease.